Welcome back. We have two problems for the tutorial in this week. The first problem is a machine tool having a mass of 1000 kilogram and a mass moment of inertia 300 kilogram meter squared is supported on elastic supports as shown in figure. If the stiffness of the supports are given by K1 3000 and K2 2000 Newton per millimeter, and the supports are located at L1, which is zero point 0.5 meter, and L2 0.8 meter. Find the natural frequencies and mode shapes of the machine tool. So we deal with a system with 2 degrees of freedom, as you can see, and we can consider different sets of coordinates to extract the equation of motion for this system. So here in the problem, it's not mentioned that which coordinates should be considered. So you are free, you can consider any set of coordinate system. I mean x1 and x2, for example, the displacement of this point and this point, or you can use the displacement of the mass center and the rotation about the mass center, or any other type of coordinates. It's up to you, but here I use the displacement of the mass center and rotation about the mass center, x and theta. As you can see, x is the displacement or deflection of the mass center, and theta is rotation about this point. So the force in the spring located in the left is K1 times by x minus L1 theta, because theta is in clockwise direction and the displacement of x is in downward direction. So this point, due to the rotation theta, will go up, but due to the displacement x will go down. So the force in the spring is equal to K1 times by the difference between these two displacement, x minus L1 theta. And because the direction is considered in upward direction, so we assume that this direction is due to the displacement x. So L theta, which of course L1 theta, which in upward direction will decrease from this value. But for K2, at this point, the displacement due to the theta will be in downward direction, and also x is in downward direction, so it will be x plus L2 theta. Now we can write the moment equation and force equation for this mass, because we have xt. So x is in vertical direction, the displacement in vertical direction, so we should write the force equation in vertical direction. As you can see, summation of the force in vertical direction, which is called x, must be equal to the mass times by x double dot. And also we have the rotation about this point, because this is the mass center, so the moment about this point is equal to the mass moment of inertia times by angular acceleration, which is theta double dot. So this is two equations of motion, and we can write, and then we need to simplify these equations. Here you can see the next step, we substitute the numerical values. As you can see, the first equation, we have x double dot and x and theta. In the second equation, we have theta double dot, x and theta. So in this system, according to this coordinate system, we have the static or elastic coupling, but we don't have dynamic coupling. So we can substitute the numerical values and finally extract the matrix M and K, the matrix mass matrix and the stiffness matrix. To obtain the natural frequencies and mode shape, we need to form the matrix of coefficient, which is K minus M omega squared, to obtain the natural frequency omega. And the determinant of this matrix must be equal to 0 to extract the frequency equation or characteristic equation. So we can do this procedure. It's similar to the examples that we solved during the lectures. This is the determinant of the matrix of coefficient, it must be equal to 0. If you simplify this determinant, you can extract an algebraic equation from order 4. As you can see here, we need to substitute omega squared is equal to alpha, and when you substitute omega squared is equal to alpha, we will have an algebraic equation from order 2. And when you solve this equation, you can easily obtain alpha 1 and alpha 2, which are the roots of the characteristic equation, and then omega 1, which is a square root of alpha 1, and omega 2, which is a square root of alpha 2. These are the natural frequencies for the system. As you can see, the first natural frequency is 2.2 and the second one is 2.6. Now we can substitute into the equation omega is equal to omega 1 in this equation here. I didn't write the equation here. This is in this equation we have the matrix of coefficient, which is k minus m omega squared. Of course, k and m are matrix multiplied by x1 and x2, and it's equal to 0. In this equation, you need to substitute omega is equal to omega 1 instead of this omega. Once we need to substitute omega 1, as you can see here, and we can extract one equation with two unknowns, x1 and x2. Of course, x2 is theta and x1 is x. So we can substitute and extract this equation, and finally we can find a relation for x and theta. This is the first mode shape. The second mode shape, we need to substitute omega is equal to omega 2, and then here when you substitute omega is equal to omega 2, which is 2.6, and simplify it, you can extract the second relation between x and theta, and this is the second mode shape. So the first mode shape, instead of x we substitute minus 5.35 this term multiplied by theta, and instead of theta we have 1. And the second mode shape is, instead of x we substitute 0.056, as you can see, for x, and theta is again equal to 1. So this is the first and second mode shape and the natural frequencies of the system. If you change the coordinate system, definitely the natural frequency will be the same. I mean, omega 1 and omega 2 will be the same, but the mode shapes will be different, definitely, because x and theta will be different. So the relation between the amplitudes will be changed, but the natural frequencies are the same, because the natural frequency is the characteristic of your system. So you can check here by using the natural frequencies, the accuracy and the results of your coordinate system. The second problem, we have two pendulums which are connected with a spring. One pendulum is with length L1 and the other one is with length L2. The mass in the first pendulum is M1 and the second one is M2. They are connected with a simple spring. We need to extract the equation of motion and then obtain the natural frequencies and the mode shapes for this system. Similar to the previous example, to write the equation of motion, we can use the Newton's second law. We should plot the free body diagram. As you can see, this is for mass M1 and for mass M2. And then we can write the moment equation about the rotation point. So here, this is the fixed point of rotation. We assume that we have a small displacement or a small theta. So sine theta can be approximately equal to theta, and cosine theta is approximately equal to 1. And we can write the moment equation for the first mass. Also, we have a tension here, but because this force or this tension passed through the point of rotation, so it doesn't have any moment, only the weight and the force due to the spring will appear in the equation of motion. And finally, it must be equal to the mass moment of inertia times by the angular acceleration. The mass moment of inertia for a particle about this point, you know, is equal to md squared, which d here in the first pendulum is L1 and in the second pendulum is L2. So we need to substitute and simplify. Easily you can extract the equation of motion by writing the moment equation for both pendulum about the mass center. And for the spring, please pay attention that because theta 1 and theta 2, both of them are in counterclockwise direction, so when we assume that both masses are moving in the positive direction of theta, here the mass m1 will go to the right, the mass m2 will go to the right as well. So if we assume that this is the direction of the force, the force in the spring, it's equal to k times by L1 theta 1 minus L2 theta 2, because this point is create compression in the spring, but this point, because it's moving to the right, will create tension in the spring. So here we assume that the force is in compression. So K is L1 theta 1 minus L2 theta 2. So L1 theta 1, which is in right direction and create compression, will be positive, but L2 theta 2, which is moving to the right and will create extension in the spring, will be with negative sign, because we assume compression for the direction of the force. So this is the direction of the spring, and we can write easily the moment equation for both masses and extract the equation of motion, as you can see here. This is the first equation. And second equation, again, if you compare, in the first equation we have theta 1 double dot, theta 1 and theta 2. In the second equation we have theta 2 double dot, theta 1 and theta 2. So this system has static coupling, but there is no dynamic coupling in the equation of motion. We can extract the matrix M and K, the matrix of masses, which is the coefficient of theta double dot, and the matrix K, the stiffness, which is the coefficient of theta. And if you substitute the numerical value, you can form the characteristic equations by using the matrix of coefficient, which is K minus M omega squared. So we have matrix K in numerical value and matrix M. So matrix K minus M omega squared can be easily obtained. And now the determinant of this matrix must be equal to 0 to form the characteristic or frequency equation. Here you can see this is the characteristic equation. If you simplify this, we will have an algebraic equation from order 4. Again, you need to substitute omega squared is equal to alpha and solve an algebraic equation from order 2 in terms of alpha. And omega 1 is equal to square root of alpha 1, and omega 2 is equal to square root of alpha 2, which are alpha 1 and alpha 2 are the roots of characteristic equations. Now you need to substitute omega is equal to omega 1 in this matrix again. Here we have the matrix of coefficient, which is K minus M omega squared multiplied by theta 1 and theta 2. It's equal to 0. Of course, this is a vector. So from each of these equations, you can, when you substitute omega is equal to omega 1, you can find this relation. Theta 1 is equal to 0.8 times by theta 2. And again, if you substitute omega is equal to omega 2, you can extract this relation between theta 1 and theta 2, which is minus 0.6 times by theta 2. The first one is the first mole shape, and second one is the second mole shape, as you can see here. Okay, so this is the procedure. I mean, when you extract the equation of motion, the natural frequency and mole shapes will be obtained similar to the previous example, and you need to solve an algebraic equation to obtain the natural frequencies. Okay, any question? Is it clear? No questions?
No question, sir.
Okay, if you don't have any question, we can wrap up this session.
Okay, sir. Thank you.
Okay, thank you.